Thank you very much, Felix, for the kind introduction. Yes, so as Felix said, I will give a brief overview over thermal scanning probe lithography throughout the next 30 minutes. As Felix mentioned already, we have published a review paper about thermal scanning probe lithography, and which covers different TSPL techniques and principles of patterning, and discusses important issues such as the heat transfer in TSPL. The review paper also focuses on various materials that have been used and provides an extensive list of materials that have been modified with heated probes. Furthermore, it gives an overview over micro and nanofabrication techniques that have been adopted specifically for TSPL, and such as reactive ion etching or lift-off processes. So the aim of the paper is really to give the reader an overview of the best approach for solving certain nanofabrication challenge with TSPL. Let us dive right into the reasons why TSPL is an excellent technique for direct write nanofabrication. First, it uses as a stimulus heat instead of charged particles, which means that structuring of low-dimensional materials and devices is possible without inducing defects, such as trapped charges. The technique reaches a lateral resolution of less than 10 nanometers in a single fabrication step. And 3D patterning is straightforward and directly related to the indentation depth of the tip. A major advantage of TSPL is that the cold tip can be used as an AFM to image the surface topography. Therefore, overlay of patterns on structured substrates or stitching is possible without the need for alignment markers. Even monolayers of 2D materials can be detected under a thick layer of resist. In the following slides, I will give a brief look at the ABCs of thermal scanning probe lithography. For those who have not yet worked with a nanofraser or attended the talk last week from Felix, first, what is TSPL and how does it work? In principle, it's very simple. TSPL is a nanofabrication technique where a heated tip is used to create nanoscale modifications into a substrate. Typically, the tip is mounted on a cantilever and brought to a temperature with an integrated heater. Then the sample is then patterned by scanning it relative to the tip. It's worth to start with a look at the two extremes in terms of the length scales. The tip apex of a thermal scanning probe is on the order of 10 nanometer and determines the resolution. The other extreme is a substrate. Let's assume we use a 4-inch silicon wafer as a substrate. Hence, the size of the substrate is 10 million times larger. This has two important implications. On the one hand, it takes a very long time to pattern a 4-inch wafer with a single tip due to the scanning speed and also the size. But on the other hand, due to the large size of the substrate, it acts as a huge heat sink, and hence only the material directly in contact with the tip is heated. This is good news because a significant temperature increase is only achieved right under the tip apex and allows for creating structures at a very high resolution. Clearly, the temperature is an important parameter in TSPL as it defines whether patterning occurs or not. Hence, it's vital to understand which parameters affect the temperature. First, the maximum temperature is limited by the heating power of the heater in the cantilever. With modern resistive silicon heaters, temperatures of 1200 degrees Celsius can be easily achieved. But the more interesting is the temperature at the tip sample contact, which is typically much lower than the heater temperature. The first important parameter is the thermal conductivity of the tip and the film and the substrate, which determine the temperature at the contact. So to calculate the temperature of a thin film at the tip sample contact, often a thermal resistance model is used. The heat transfer from the microheater through the tip apex into the substrate can be modeled as illustrated in the sketch. Based on this model, the tip sample contact can be expressed as a function of the heated temperature as well as the substrate temperature and the thermal resistances. For simplicity, in this model, we neglect the heat transfer through the air gap. And then the heating efficiency C here is the ratio between the substrate resistance and the sum of all thermal resistances, and determines how much heat is transferred into the film. So on the one hand, higher tip resistance and higher contact resistance decreases the heating efficiency. On the other hand, a higher substrate thermal resistance increases the heating efficiency and hence the contact temperature. So in case of a 4-inch silicon wafer, we have seen that the substrate is huge in comparison to the heated tip and acts as an efficient heat sink. So in order to heat a thin film to temperature largest than the substrate, the film material should be a good thermal insulator. Luckily, this is the case for most polymers. Let's have a look how the tip size, the tip sample contact, and the film thickness affect the temperature. Due to the small size of the tip towards the end, the heat flow is reduced. This is because the tip dimension is smaller than the mean free path of phonons. The consequence is that with a blunt tip, higher temperatures can be achieved than with a sharp tip. But in TSPL, to reach high resolution, a sharp tip is often required. For those who have worked with the nanophaser, this effect can be experienced when blunt tips are used, which are typically good to write deeper patterns or larger areas. So the heat transfer across the tip sample interface is a parameter that is most difficult to calculate or to measure. It depends on the atomic roughness of the tip and the sample and how efficiently phonons can be transferred between the two materials, the tip and the film. So calculating the contact resistance is further complicated because during patterning, it can change due to tip wear and contaminations. The film thickness is important for the thermal isolation in order to reach reasonable temperatures of a few hundred degrees, as discussed before. And the thickness, as the thickness of the film decreases, the influence of the thermal conductivity of the substrate becomes more important. Typically, a couple of tens of nanometers of a polymer film on a silicon wafer are already enough to reach sufficiently high temperatures at the interface. The next question is, what happens when the material under the tip is heated to a certain temperature? I mean, we want to trigger a reaction or a change in the material. Therefore, let's look at the main parameters that affect such reactions. The most important parameter is the temperature. For example, for a simple thermal degradation reaction, the kinetics can be described by a first-order rate equation, as shown in the slide. The relative amount of converted material, alpha, can be expressed as a double exponential function with respect to the temperature. The conversion function or the reaction function is plotted as a function of the temperature. The circles here indicate 1%, 50%, and 90% completion of the reaction. Because the temperature, because the conversion does not depend linearly on the temperature, often the higher resolution can be achieved with the conversion than it would be assumed from the distribution of the temperature. This is good news because it allows for high resolution patterning. Another parameter is the activation energy of the reaction. The higher the activation energy, the more heat is necessary to induce the reaction, and hence the higher the temperature needed to complete the reaction, as can be seen in the figure. In the graph, one can see that the reaction curve shifts towards higher temperatures with increasing activation energy. The temperature necessary for a reaction increases linearly with the activation energy, as can be seen in the right graph. As a general rule, reactions with low activation energies are preferred for thermal scanning probe lithography. The third important parameter is the contact time between the tip and the sample. As can be seen in the graph, for shorter tip sample contact times, the reaction curve shifts towards higher temperatures. The temperature necessary to complete the reaction depends logarithmically on the heating time, or in other words, the faster the writing speed, or the shorter the contact time, the higher the temperature that is necessary to complete the reaction. This is the reason why for TSPO often higher temperatures are necessary to complete the reaction within a few microseconds as compared to the macro scale where much longer heating times are used. Closely related to the reaction is the question, which materials are best suited for TSPL, which materials, show which kind of reactions. Most of the materials that have been used are polymers. This is because polymers typically require low temperatures to induce some modifications. Molecular glasses have been as well extensively researched as thermal resists. And more recently, 2D materials have gained interest for nanofabrication with thermal probes. Chalcocyanide films have also been used to induce phase changes with heated probes, as well as sol-gel films for ferroelectric and magnetic materials have been used to induce crystallization with tips. Even metals have been processed by TSPL. As a basic requirement for a material to be useful for thermal scanning probe lithography is that there exists a thermally activated process in a temperature range which can be reached by TSPL. We have seen that the temperature can be considerably higher, necessary to induce a reaction can be considerably higher for TSPL than at the macroscopic scale. So to create high resolution patterns, it is also necessary that the material can form flat films and does not contaminate the tip. And if patterning speed is a criteria, the reaction should be completed within less than 100 microseconds under the tip. With the materials that have been researched in the literature, we found there are 3 types of sample modifications: removal, conversion, and addition. Each modification includes different processes such as indentation, sublimation for removal, physical and chemical conversion of the material, or addition via melt transfer or from the gas phase. And we separated the modifications in these 3 different categories because there are different challenges in terms of the fabrication related to each of these groups. So in the first group, removal, we want to bring something away from the substrate without redeposition. Whereas in the conversion, we would like to convert a material without considerably changing the topography. And in addition, one has the challenge to bring something up to the substrate with the heated tip. So let's first look at the removal by sublimation. In this process, material is sublimated from the substrate by local heating with the tip. For nanofabrication, it's important that the material is removed from the substrate without leaving residues or redeposition near the patterns. The aim is to create a topography contrast which can then be transferred into a useful material such as silicon or silicon oxide. And sublimation can be achieved with specifically thermosensitive resists, And we'll briefly have a look at two examples of such thermosensitive resists. One example is molecular glasses, and the other is polyphthalaldehyde. Molecular glasses form a solid at room temperature through hydrogen interactions. These molecules require only little activation energy to sublimate from the surface. Although they would be ideal for TSBL, these classes of materials have not yet overcome certain challenges to be a good resist for nanofabrication. And the second material, polyphthalaldehyde, which is a polymer that decomposes by a self-amplified decomposition reaction, provides a much cleaner way of removing it from the surface. And this, due to this special self-amplified decomposition, the polymer decomposes differently than normal polymers such as PMMA via a rapid decomposition process, and it decomposes into volatile monomers without melting. This is important because this reduces the contamination on the tip apex. Besides the clean decomposition of this resist, it exhibits also a reasonable shelf lifetime and can resist chemical etching with standard transfer processes. Hence, it is currently the most used thermal resist. And the examples that I'm going to show in the following slides are often performed with polyphthalaldehyde. So for removal, a large process library exists already. Depending on the number of layers, different resolutions and modifications are possible. For a single layer, patterns directly written into PPA can be used for writing traps or precisely tailored 3D landscapes for assembly of nanoparticles. And it has also been shown that the patterns can be directly the patterns can be directly used for molding or plating to create masters for nanoimprint lithography. And the pattern can also be directly etched into, for example, silicon oxide. However, PPA has a limited etch resistance, and due to the conical shape of the tip, it's only allowed to to create shallow patterns with thermal scanning probe lithography. Therefore, in order to create deeper patterns, second layer is typically added. So with 2 layers, an amplification of the pattern in the thermosensitive resist can be achieved, and much deeper structures can be fabricated. For this, for 2 layers, it's also possible to make a lift-off process. For example, deposit metal contacts on a material, and after opening the PPA on the top, with a wet etch process, the transfer layer an undercut can be created in the transfer layer, and then the position of metal on top can be achieved, and via stripping the resist is then removed. And another application of the 2 layers is that one can selectively activate a functional material under the thermosensitive resist. So for example, in this case, a material is protected under the PPA, and the PPA is opened, and then, for example, with an oxygen plasma treatment, the material can be activated and the PPA can be removed afterwards. And like this, selective nanostructures on the surface can be created. To achieve highest resolution possible, it is often required to have 3 layers, and there it's necessary to have an approximately 2 to 3 nanometer thick hard mask between the PPA and the organic transfer layer. But also here, deep etching and high resolution lift-off are possible. Heat can also be used as a stimulus to trigger a chemical reaction or facilitate the movement of atoms to, for example, induce phase changes. In the following, I would like to provide a brief overview of the conversion processes that have been used in literature. First example uses heat to locally deprotect functional groups on the surface of polymers by TSPL. This offers a unique way to selectively modify a sample surface chemistry, for instance, to locally uncover functional groups such as amine or hydroxyl groups. The deprotected groups can then be used to bind nanoparticles, proteins, or enzymes, for example. This technique is particularly interesting for biomedical applications. Another technique that has been often used in literature is the local conversion of a precursor material into a functional material. A few examples are reduction of graphene oxide to create conductive nanocircuits of reduced graphene oxide, or the fabrication of organic pentasynthesis from a precursor material. Recently, a new unique application of TSPL have emerged, where heat from the tip is used to locally modify polarization of magnetic domains by heating magnetic multilayer films under application of an external magnetic field. Another example is crystallization of nanoscale areas with a heated tip. And here, chalcogranite films are best suited for such applications. Ferroelectric magnetic nanostructures have also been fabricated from salt shell-based thin films. However, these processes require rather long annealing times on the order of milliseconds to seconds. And the opposite phase transition from crystallite to amorphous is also possible. The fast heating and cooling rates attainable by TSPL enable local quenching at the nanometer scale. And here I would like to bring in a short example, an own study that we performed. We did local quenching of organic material. We used, for this case, supramolecular polymer, which is a polymer that is where the monomer units are not linked by a covalent bond, but by hydrogen interactions. In this work, we explored this supramolecular polymer by TSPL and found that the fast cooling rates with TSPL allow processes which are not possible at the macro scale. So the material is a fluorescent, a supramolecular polymer, and the monomer can form aggregates which change the fluorescent color in the material. On the macrometer scale, when the material is at room temperature, it fluoresces in red. And when the material is melted above the melting temperature, it starts to fluoresce in green. This is due to the disaggregation of the monomers at high temperatures. This effect is reversible, and at room temperature, when cooled, the fluorescence is always red. However, at the nanometer scale, when a heated tip is used to heat only small volumes, the heat quickly dissipates into the sample after the probe has been removed. Quenching of this high temperature state can induce a permanent fluorescence contrast. This is an example where the high heating rates of TSPL is important, and I assume that there will be other materials that exhibit such a behavior that is not possible at the macro scale. So the third modification is addition. So besides removal and conversion, one can also add material with thermal scanning probe. And one common method used is where a heated tip is loaded with a low melting temperature material, such as a polymer or indium, a metal with a low melting temperature. And when the tip is heated and brought into contact with the substrate, a flux of the melt is established across the tip sample contact. And then scanning the tip over the substrate creates arbitrary patterns that can be used for pattern transfer with standard lithography techniques such as dry etching. Basically similar techniques as discussed for the removal. During our literature research, we found one publication that used a heated tip for local chemical vapor deposition to deposit copper and copper oxide nanostructures. So here, a precursor is collected from the gas phase, from the environment, and solidified through a chemical reaction on the substrate. And one can also imagine that the tip can be used to locally dope material under the tip with a suitable dopant from the gas phase. So here, many possibilities are yet unexplored. Now, I'd like to draw a comparison between the different TSBL techniques. It shows that the highest resolution can be achieved with removal and conversion, ranging to resolutions down to 8 nanometer half-pitch size. Here, the limiting factor in terms of resolution is the tip apex radius. For addition, of course, the tip shape is important, but also the melt flow and the surface tension play an important role for achieving high resolutions. The highest speed of 20 millimeter per second has been demonstrated for PPA sublimation, and the typical speed ranges between 0.1 to 1 millimeter per second. For conversion, slightly lower speeds have been achieved. For addition, however, the patterning speed is significantly lower. This can be explained by the fact that material has to be transferred typically from the tip to the substrate. In terms of maturity, the most mature technique is removal with a commercial resist PPA, for which we have seen that many fabrication processes exist, and also the commercial resist is available. But for conversion, many materials have been converted in the literature by TSBL, but only few established processes exist beyond research in universities. Addition of material is still in a very exploratory phase, with only few people that master this technique. So this leads me to the challenges of TSBL. So one of the challenges is to determine the tip sample contact temperature, which is difficult to compute. In particular, for understanding the thermal processes at the nanometer, at the nanoscale, the temperature knowledge of the temperature is very valuable. However, for patterning, for example, knowledge of the temperature is not necessary, because the feedback from the topography changes is often enough to determine if a reaction took place. That is why it's nice that with TSBL, one can use the cold tip to scan the substrate and directly detect whether a modification took place. A more important issue is degradation and contamination of the tip. Here, the focus is on developing resist materials that convert or decompose without leaving residues on the tip. And finally, in order to become industrially relevant, the throughput of TSBL has to be increased. Solutions towards increasing the throughput exist, such as increasing the number of tips that can be actuated in parallel. Hybrid thermal lithography, where a laser and a tip are used in the same tool, is another strategy. That leads me to my last slide, the take-home message. So with a heated probe, one can remove, convert, or add material to a substrate. And TSBL can do that very fast. For TSBL, many adopted nano microfabrication processes exist today, and one can select from a huge library of processes. However, despite there are many materials that have been used, there's still a wide range of unexplored materials, and there are quite some opportunities to do some materials research. That leads me to the end of my presentation. Thank you for your attention.